Somewhere in your home there is a coin, and it is either heads or tails right now. Nobody looking, nobody touching, a quiet fact in the dark. It is the safest claim you will hear today. Physics has spent 40 years putting it on trial, and the claim keeps losing. In one laboratory, by 84 standard deviations. Tonight, the inequality that puts a number on really there, an atom that crossed a room on no path at all, and the loophole still keeping your coin honest. Check the coin. It will be heads or it will be tails, and the moment you see it, you will feel the whole question evaporate. Of course, it was already one or the other. What else could it have been? Hold that feeling, because tonight is the story of how that exact certainty, the most innocent assumption a mind can make, was dragged out of philosophy, converted into an arithmetic statement, wired into superconducting circuits, cesium atoms, diamonds, beams of neutrinos fired through 700 kilometers of rock, and tested. It has a name now: macrorealism. The doctrine that a macroscopic thing with several states available to it is, at every moment, actually in one of them, watched or unwatched. And tonight is equally the story of what the tests did and did not find, told with a precision the topic almost never receives, because the honest result is stranger than the slogan. The slogan says the world dissolves when unobserved. The data say something more careful and, in its way, more unsettling. The innocent picture has failed every test it has ever been given, at every scale we can reach, and no one has found the line where it becomes safe again. Between your coin and the smallest things in existence, there is supposed to be a border where quantum strangeness ends and honest, definite facts begin. Tonight we go looking for that border with the people who have spent careers hunting it. Keep the coin where you can see it. By the end, you will know exactly what physics can still promise about it, and you will meet the one loophole through which its innocence survives. The trial has an origin story, and it begins, as the deepest quantum stories usually do, with Einstein on a walk. His companion was Abraham Pais, a younger physicist who would become one of the great historians of the field, and the walk took place in Princeton, in the years when quantum mechanics had already conquered every laboratory it touched. Einstein, who had helped build the theory and then spent decades interrogating it, suddenly stopped. He turned to Pais and asked. Pais would later print the moment in Reviews of Modern Physics, so we have it in his own words, whether Pais really believed that the moon exists only when he looks at it. It is the perfect question. And notice what makes it perfect. Its absurdity is the argument. Of course the moon is there. Whatever the quantum equations say about electrons, that they hold no definite position until measured, that they pass through two slits at once, that their properties crystallize only at the moment of observation, surely all of that is bookkeeping about the very small. Surely it stops before it reaches moons, mountains, coins. Einstein died believing the strangeness had to stop, that quantum mechanics was a spectacular but incomplete accounting, beneath which the world kept definite books. And for 30 years after that walk, his questions stayed where he left it, unanswerable, a matter of taste, the kind of thing physicists argued about at dinner and then set aside, because nobody could imagine an experiment that would decide it. Before meeting them, slow down and take inventory of what you actually believe about the coin, because the belief has moving parts, and tonight we'll dismantle them separately. Part 1. The coin has a definite face-up state at every instant. Not a probability, not a tendency. An actual fact, holding steady in the dark. Part 2. Checking is innocent. Lifting your palm reveals the fact without manufacturing it. The looking and the being are separate transactions. Part 3. So obvious it hides. The fact belongs to the world, not to you. Anyone who checks gets the same answer, because there is one answer, out there, owned by no one. Now ask yourself honestly, which of those three would you surrender first if arithmetic forced a sale? Could you imagine a world where things are definite, but every act of checking shoves them? Where checking is innocent, but there was nothing definite to check? Where facts exist, but each observer holds their own? Keep your answer. Tonight ends with all three options alive, priced, and on the table. And the one thing not on the table is keeping all three parts for free. What does it mean that the most automatic belief you own turns out to be three separate claims, no two of which the universe has agreed to honor together? Then, in 1985, two physicists did the thing that changes everything in science. They found a way to make the dinner argument pay rent. They took Einstein's question about the moon, is it there when nobody looks? Shrank it onto a piece of laboratory hardware, and converted it into an inequality, a plain arithmetic statement built from nothing but measured numbers that must hold if the innocent picture is true and can fail if it is not. No philosophy in the test, just counts, correlations, and a threshold. Cross it, and some part of the innocent picture is mathematically dead. Their names were Anthony Leggett and Anupam Garg. The title of their paper asked bluntly, "Is the flux there when nobody looks?" And to understand the trap they built, you first have to appreciate what they were up against. Because the obvious experiment, just check whether things are there when you are not looking, eats itself. Look and you are looking. How do you photograph the unphotographed? How do you audit a room's contents on the condition that no one enters the room? Every direct assault on the question collapses into performing the very act the question excludes, which is precisely why 3 centuries of scientists filed it under philosophy and moved on. Think about how a trap for such a question would even have to work. It cannot inspect the unobserved moment directly. That is forbidden by construction. It can only surround the moment, measure before, measure after, and ask whether the pattern of correlations across the surrounding checks is consistent with something definite having existed in the gap. The unobserved interval gets interrogated the way a detective interrogates a locked room, never by entering, only through the accounts of the witnesses posted at the doors. The genius of 1985 was proving that the witnesses' accounts, all by themselves, can convict. Anthony Leggett was, even then, one of the deepest thinkers alive on the quantum theory of large things. The physics of superfluids and superconductors would later bring him the Nobel Prize. He carried a conviction rare among his colleagues, that the reach of quantum mechanics into the macroscopic world was not a settled question, but an untested one, and that physics had no right to an opinion it had not paid for experimentally. With Anupam Garg, he built the payment scheme. Their inspiration was Bell's theorem, the 1964 result that had turned the Einstein versus quantum argument about distant particles into a measurable inequality. But where Bell compared 2 particles at 2 places, Leggett and Garg made a swap of breathtaking economy. They compared one system with itself at different times. A Bell test asks whether correlations across space are too strong for any local, definite story. The leggett-garg test asks whether correlations across time are too strong for any story in which the system actually is somewhere, all along, and can be checked without being shoved. Physicists call it, half affectionately, the Bell inequality in time. Here is the machine, and it is simple enough to build in your head. Take any system that is always in one of 2 conditions, a coin that is heads or tails, a current flowing clockwise or counterclockwise, anything binary. Call the value Q and score it +1 for the first condition, -1 for the second. Now pick 3 moments, time 1, time 2, time 3, and, over many repeated runs, measure the correlations between pairs of moments, how strongly the value at one time predicts the value at another. Each correlation is just an average of products of plus and minus ones, so each lives between -1 and +1. And now the knight's first equation, the trap itself. Before the symbols, it says that for any system that really is in a definite state at every moment, and whose gentle measurement does not disturb what follows, a particular combination of those 3 correlations can never exceed 1. The equation reads K3 equals C12 plus C23 minus C13, and K3 stays at or below 1. Feel why with coins. If the value at time 1 agrees strongly with time 2, and time 2 agrees strongly with time 3, then time 1 and time 3 are forced into agreement too. The minus sign punishes any story where the ends disagree while the middle agrees with both. Try to break it with any definite sequence. Heads, heads, tails, tails, heads, tails, any pattern, any probabilities, and the arithmetic holds you at 1. It is not physics yet. It is bookkeeping as inescapable as the fact that you cannot be taller than your father and shorter than your son, while your father is shorter than your son. Any world of definite, gently checkable facts lives at or below 1 forever. Quantum mechanics, asked the same question, does not live below 1. Run the quantum calculation for a 2-state system oscillating between its states, the standard textbook evolution. Choose the 3 measurement moments wisely, and the predicted K3 climbs to 1.5. Not by a hair, 50% above the classical ceiling, a violation as flagrant as arithmetic allows for such a system. There is even a theorem, the temporal cousin of the Tsirelson bound, fixing 3/2 as quantum theory's own maximum for this test. Stop and absorb what the gap between 1 and 1.5 means. Below the line. Every possible world in which your coin is definitely something and looking gently changes nothing. Above the line. No such world, full stop. No assignment of definite values to unmeasured moments, however clever, however conspiratorial, can produce those correlations under those assumptions. The number is a border between metaphysics, drawn in arithmetic. For the first time since Einstein stopped on that walk, is it there when nobody looks, had an answer sheet. All that remained, was to run the test. Which is where the story becomes an engineering epic, because the 2 assumptions behind the inequality carry names that will matter enormously by the end of tonight. And building an experiment that honors both nearly defeated a generation of physicists. Assumption 1. Macrorealism per se. The thing is always actually in one of its states. Assumption 2. Non-invasive measurability. You can find out which without kicking the system onto a new course. Keep both in view. The entire meaning of everything that follows hangs on the word and between them. Pause here, because there is something worth savouring in what Leggett and Garg had done before any laboratory fired a single shot. They had taken the most protected belief in the human inventory, the sheer there-ness of the world, and shown it had consequences, numerical, checkable, falsifiable consequences. Philosophy asks what exists when nobody looks. Physics, after 1985, could ask instead what correlations survive between Tuesday's numbers and Thursday's. And the humble bookkeeping question carries the grand one inside it. If you have ever wondered what separates science from every other way of knowing, it is exactly this maneuver. The conversion of an endless argument into a threshold that reality itself gets to cross or respect. If nights spent watching that conversion happen are something you value, consider subscribing. It helps these deep dives reach more curious minds. Now, the engineering epic. To run the test on something genuinely large was Leggett's dream, and the obstacle was the same monster this channel has met before, decoherence. A big system leaks information into its surroundings almost instantly, and the leak destroys exactly the delicate quantum correlations the test is hunting. What was needed was an object macroscopic enough to mean something, yet isolated enough to stay quantum across 3 measurements. The candidate Leggett had championed since the 80s was as strange as the question: a loop of superconducting wire, cooled to thousandths of a degree, in which billions of electrons flow together as a single collective current, clockwise or counterclockwise. 2 states. Macroscopic by any laboratory standard, a real amperage-carrying current you could draw on a circuit diagram. And, if quantum mechanics truly scales, capable of something no coin has ever been accused of, flowing both ways at once. Pause on the phrase macroscopic quantum object, because it should sound like a contradiction, and the fact that it is not, that such things can be manufactured to order in laboratories on 3 continents, is a story tonight cannot skip. It begins with a resistanceless trick a century old. Cool certain metals within a few degrees of absolute zero, and their electrons stop behaving as a crowd of individuals. They pair up, and the pairs condense, every pair described by one single shared quantum wave, the way every soldier in a marching column shares one cadence. That is superconductivity, and its deep meaning is larger than free electricity. It is quantum mechanics refusing to stay microscopic. A superconducting current is billions upon billions of electrons whose collective motion is written in a single wave function with a definite quantum phase. One wave, the size of a circuit, obeying the same equations as one electron. Bend such a wire into a loop, interrupt it with whisper-thin insulating barriers, Josephson junctions, through which the collective wave quantum tunnels, and you have built the device at the heart of tonight's grandest experiments. A flux qubit, a circuit whose 2 available states are a persistent current circulating clockwise and the same current circulating counterclockwise. Not 2 electrons disagreeing, 2 opposite motions of the entire electron sea. The current is real in the fullest engineering sense, 170 nanoamperes, the kind of number found on datasheets and measured with commercial instruments. And quantum mechanics, if it truly has no scale limit, says that loop can occupy a superposition of both circulations. Billions of particles flowing in 2 opposite directions at once as a single quantum fact. Why does anyone believe such an outrageous claim enough to test it? Because the circuits sing. Drive a flux qubit with microwaves and it performs Rabi oscillations, the clean sinusoidal cycling between its 2 states that is the unmistakable signature of a genuine 2-level quantum system. The same dance a single atom performs in a light field. Measure the energy levels and they are split exactly as superposition theory demands. The clockwise and counterclockwise states hybridizing into combinations, their energies repelling, a spectrum that has no classical explanation whatsoever. By the time the leggett-garg campaign reached these devices, superconducting circuits were already the workhorses of the young quantum computing industry. Engineered, characterized, mass-produced quantum objects, their coherence times improving year over year. The whole edifice of that industry resting on the premise that macroscopic circuit variables genuinely superpose. Every quantum computer in every corporate laboratory is, in this sense, a standing wager against macrorealism. But an industry's working assumption is not a foundational test. The machines would compute just the same if some subtle macrorealist story mimicked superposition in every engineering respect. That is exactly the gap the leggett-garg inequality was built to close. Not does the circuit behave usefully quantum, but can any definite state, gently measured account of this circuit, any at all, reproduce its correlations in time? The industry assumes. The inequality checks. There is a human thread here worth pulling, because the flux qubit is not a random choice of arena. It is Leggett's own decades-long obsession made silicon. From the 1980s onward, against a community that mostly considered the matter settled by decoherence's obvious ferocity, Leggett insisted that quantum mechanics owed us a demonstration at the scale of collective, macroscopic variables, currents, voltages, the motions of things. He championed superconducting devices as the arena where the demonstration, or its refutation, would come. He even coined a measure for the argument: disconnectivity. How many particles must be described as jointly, irreducibly quantum for a given state, precisely to distinguish a mere many-particle system from a genuinely macroscopic superposition. When the 2016 experiment ruled out the definite current picture at 84 standard deviations with his name on the author list, it closed a personal circle 4 decades wide. The theorist who had refused to let physics assume its most important answer lived to watch the question he formalized in 1985 answered, for that system, at that scale, in his favor and against his own championed possibility that quantum mechanics might fail. Science contains few stories of that shape. A man who built the gallows for his community's assumption, tested it for 40 years, and reported at the end that the assumption survived every drop, and the innocent picture did not. What does it mean when the most rigorous doubter a theory ever had becomes the byline on its most crushing vindication? It took a quarter of a century from the 1985 paper to the first genuine violation, and the delay itself is a lesson in how hard nature makes this question. The breakthrough came in 2010 from the Quantronics group at Saclay, outside Paris. Agustin Palacios-Laloy and colleagues, building on a theory of gentle measurement worked out by Alexander Korotkov. Their system was a transmon, a superconducting circuit behaving as a single artificial atom, driven so that it cycled smoothly between its two states, the clean, textbook oscillation the inequality was built for. And their solution to the central dilemma, how do you measure without kicking, was the quiet revolution of the experiment. Instead of interrogating the circuit sharply, collapsing it onto one answer, they coupled it weakly to a microwave resonator and listened continuously to the faint shadow the circuit cast on the passing microwaves. It was a measurement so soft it extracted only a whisper of information at each instant, disturbing the evolution as little as quantum theory permits. From that continuous whisper, they reconstructed the correlations between the circuit's state at different times, assembled K3, and compared it to the classical ceiling of 1. The result? The ceiling broke, by 5 standard deviations. The correlations in time were too strong for any world in which the current was always definitely one thing and the listening did not push. Odds of a statistical accident at 5 sigma, about 1 in 3.5 million, the same threshold particle physics demands before announcing a new particle. 25 years after 2 theorists drew a line in arithmetic, a piece of laboratory hardware stepped over it. One experiment, though, is a claim, not a case, and this particular experiment carried an asterisk its own authors understood well. The argument only works if the whisper measurement truly did not push the circuit, and that gentleness was itself a quantum mechanical modeling assumption. A determined skeptic of the innocent picture must fail conclusion could dig in. Perhaps the current was always definite, and your so-called gentle listening secretly shoved it, manufacturing the correlations you triumphantly report. That escape hatch has a name, the Clumsiness Loophole, and it is not a fringe worry. It is the deepest structural weakness of the entire enterprise, coined and formalized by theorists precisely because it can never be fully welded shut. Park it in your memory. The final act of tonight walks through that hatch in slow motion. What matters for the story now is how the field responded, because the decade after 2010 became an arms race between experimenters closing the hatch and the hatch's stubborn refusal to close completely. Each new experiment attacked the same question with a different weapon, on a different system, with the disturbance controlled a different way, and the violations kept coming from every direction at once, in one of the most consistent experimental campaigns in modern physics. How gentle can a look possibly be? It is worth feeling the physics of that question, because it is the hinge the Saclay experiment turned on. Every measurement is a transaction. To learn about a system, something, a photon, a field, a current, must couple to it, and the coupling has a price the system pays. Quantum mechanics sets the exchange rate with merciless precision. The more information a probe extracts, the more it necessarily disturbs, down to a hard floor no cleverness can breach. But the exchange rate works in both directions. Extract almost nothing per glance, and you disturb almost nothing per glance. That is weak measurement, a probe coupled so faintly that each instant yields only a murmur of information, the system's evolution bending imperceptibly under the inquiry. Is a murmur enough to build a case? Alone, no. Accumulated across thousands of runs, statistically, yes. The murmurs assemble into exactly the temporal correlations the inequality consumes. The experiment is a portrait of the quantum bargain itself. You may know, or you may leave undisturbed, and the entire art is spending the trade-off wisely. The campaign's roll call deserves hearing at speed, because its diversity is the argument. Photons violated the inequality. Nuclear spins in molecules violated it. Impurity atoms in silicon violated it. And then, in 2013, a collaboration between Delft and Oxford ran a version so elegant it reads like a magic trick with the mechanism printed on the program, using a single nitrogen nuclear spin inside a diamond, and a game invented by Yakir Aharonov and Lev Weidman called the three-box paradox. Prepare a quantum particle across three boxes in a particular way, and quantum mechanics makes a pair of promises that no definite story can keep simultaneously. If you open box A looking for the particle, you will certainly find it there, and if instead you had opened box B, you would certainly have found it there. The same particle, the same preparation. Certainty in A if you ask about A, certainty in B if you ask about B. In the diamond, the promise is held, and the whole protocol was run with control experiments quantifying exactly how much classical disturbance the measurements introduced, so a skeptic could not wave the result away as clumsiness without pointing to disturbance the team had measured to be absent. The classical description died at better than 7.8 standard deviations. Where, tonight's refrain must ask for the first time, where was the particle before the box was opened? Every definite answer to that question is now arithmetic roadkill. The honest quantum answer is that the question presumes what the experiments keep executing, a fact of the matter about the unlooked at. The three-box game ran on a tool that deserves its own moment, because it is one of the strangest instruments in the quantum toolbox, and tonight's second formal equation. In 1988, Aharonov, David Albert, and Lev Weidman asked what happens if you measure so gently that a single run tells you almost nothing, and then harvest your information statistically across thousands of runs from systems prepared the same way and later found in the same final state. The quantity such a protocol delivers is called the weak value, and its formula is short enough to speak. Before the symbols, it is the overlap of the final state with the operator acting on the initial state, divided by the plane overlap of final with initial. The equation reads A weak equals the final state bra times the operator times the initial state ket, all divided by the final state bra times the initial state ket. Innocent-looking division, except that the denominator, the overlap between where the system started and where it ended, can be made tiny, and when you divide by something tiny, the result explodes. A spin whose honest possible values are plus 1/2 and minus 1/2 can register a weak value of 100. The measurement is real, repeatable, published. The number sits nowhere in the spectrum of things the property can classically be. Weak values are the quantum world caught between definite frames, evidence of what the bookkeeping looks like when you refuse to force an answer. And they are the standard machinery now used to peer into exactly the unlooked-at intervals the leggett-garg test is about. What is a property, tonight's refrain asks again, in a theory where gentle enough looking returns values the property cannot have? But the experiment that closes this chapter, the one that, for my money, is the single most beautiful test of there-ness ever performed, came from Bonn in 2015, and its weapon was absence. Carsten Robens, Andrea Alberti and colleagues trapped individual cesium atoms in an optical lattice, a crystal made of laser light, a row of luminous egg cups holding one atom, and walked each atom down the row in a quantum walk, its two internal states shunted left and right by polarized light. The leggett-garg question: does the atom, between checks, actually possess a position? Is it really somewhere, hopping a definite path like a checker on a board? And here is the move that makes the experiment unforgettable. To measure where the atom was without touching it, they performed what is called an ideal negative measurement. Aim the probe at one site only and count the runs where nothing happens. No fluorescence, no click, no photons scattered off the atom. The detector's silence is itself the information. Not here, therefore there. The atom interacted with nothing. Light never touched it. Any macrorealist must concede that a measurement consisting of no interaction whatsoever cannot have disturbed the atom's course. The loophole's own logic turned into a scalpel. Run the walk, harvest the correlations from those untouched atoms, assemble the inequality, and it breaks, by 6 standard deviations. The published conclusion is worth quoting in its full, careful violence. The result rigorously excludes, falsifies, any explanation of the atom's transport based on classical, well-defined trajectories. Sit with that. Not the path is unknown. Not the path is disturbed by observation. There is no path. A material particle, an atom of cesium, 133 nucleons, the thing your school chemistry drew as a little ball, crossed a stretch of space, and the hypothesis that it did so by being at a sequence of places was tested against the arithmetic and lost. The atom got from here to there without, in any classically meaningful sense, ever being anywhere in between. Somewhere around this point in the evening, an honest viewer starts to feel the floor tilt, so let the tilt be felt properly before the story escalates. The coin under your palm borrows all of its innocence from an intuition built out of atoms like that cesium atom. Every solid thing you trust, the table, the floor, the hand itself, is a parliament of particles for which it is definitely somewhere right now, has been tested at the single particle level and demolished, not by argument, but by counting. And yet the coin, the table, the hand feel utterly, boringly definite, and they are. Nothing tonight disputes what you will find every single time you look. The scandal is not up here at your scale. The scandal is that physics cannot yet tell you where, on the road between the cesium atom and the coin, the quantum bookkeeping hands over to the classical one, or whether it ever formally does. Which is exactly why the next chapter of the campaign aimed upward. Bigger systems, heavier objects, larger currents, a deliberate march up the mass ladder toward your coin, looking for the border. The march produced the most violent single number in tonight's story, and the man whose name is on the original 1985 Inequality was, 31 years later, an author on the paper that delivered it. The paper appeared in Nature Communications in November 2016 from a collaboration spanning NTT's labs in Japan and the University of Illinois, with George Nee and William Munro leading the analysis, and Anthony Leggett, then 78, among the authors. The man who drew the line in 1985. The man who drew the line in 1985, present in person for its most emphatic crossing. The system was his old dream made real, a superconducting flux qubit, a loop carrying a persistent current of 170 nanoamperes, billions of electrons in collective motion, a genuinely macroscopic electrical current by any engineer's standard, capable, if quantum mechanics scales, of superposing clockwise and counterclockwise flow. The protocol was built for skeptics: prepare, shuffle, measure, with the shuffle step arranged so that a macrorealist's definite current story and the quantum story make cleanly separated predictions, and with dedicated control experiments bounding how much the measurements disturb, so the clumsiness escape had to squeeze through quantified cracks rather than open doors. Then they ran it, and the definite current picture did not lose the way theories usually lose, by a respectable but arguable margin. It lost by approximately 84 standard deviations. Numbers like that deserve translation, because nothing in ordinary life prepares you for what 84 sigma means. 5 sigma, the threshold at which physics declares discoveries, the confidence behind the Higgs boson announcement, is odds of about 1 in 3.5 million that chance faked your result. At just 7 sigma, the odds pass 1 in a trillion. By 10 sigma, the number has left every everyday comparison behind. 84 sigma is not a probability anyone can meaningfully write down. The implied odds against a fluke exceed anything expressible in terms of lottery tickets, atoms in the universe, or time since the beginning of the cosmos. The mathematics of chance simply has no vocabulary left at that altitude. In practice, it is the sound of a hypothesis not merely failing a test, but being erased from the space of live options. And now, precisely because the number is so violent, tonight's honesty rule matters more than anywhere else. What was erased? Not the coin is definite. Not realism as such. What the experiment ruled out, in its author's own careful phrasing, was the family of theories that deny coherent superposition of those 170 nanoampere currents on those 10 nanosecond timescales, while explaining the data through measurement disturbance of a bounded kind. That is a mouthful, and every word of the mouthful is load-bearing. The result crushes a specific, quantified corridor of escape. It does not crush every escape. The corridor's walls are the control experiments, and a sufficiently determined macrorealist can posit disturbances hiding outside what the controls constrained. 84 sigma of violence, aimed with a jeweler's precision at a target narrower than the headline suggests. Keep both halves, because both are true, and the gap between them is where this entire subject actually lives.
Meanwhile, the campaign stretched the inequality across scales no one at that 1985 blackboard could have imagined. At MIT, Joseph Formaggio and David Kaiser realized that the test needs no laboratory at all if nature is already running one, and pointed it at neutrinos. The MINOS experiment fired a beam of them from Fermilab through 735 kilometers of solid rock to a detector in a Minnesota mine. Along the way, each neutrino oscillates between its identities, a two-state quantum evolution written across half a continent. Treat the identities as the dichotomic variable, the propagation as the time axis, and the oscillation data as the correlations, and the leggett-garg inequality can be assembled from archived measurements. It breaks, by better than 6 standard deviations in the original 2016 analysis, and here, tonight, documents a wrinkle rather than smoothing it. Later independent reanalyses, treating the energy uncertainties differently, report the MINOS violation at better than 10 sigma, a sister analysis of the Diabay reactor data near 6, and the CAMLAN data at under 2. The significance depends on the statistical machinery, which is exactly the kind of detail a channel that promises honesty owes you. The robust core survives every treatment. The correlations of a particle oscillating across 735 kilometers, the longest distance over which either the Bell or the leggett-garg question has ever been posed, are too strong for any definite identity story. The quantum refusal to be pinned down is not a tabletop phenomenon. It stretches across geography. Stop and run tonight's audit on yourself, because the numbers have been arriving fast, and it is worth noticing what they have done to the reasonable positions. Before 2010, a fair-minded person could say, the definiteness of things is untested. Believe what you like. After Saclay, after the diamond, after Bonn, after the Flux qubit, after the neutrinos, what exactly is left of that liberty? Would you bet against a 5 sigma result? Perhaps. One experiment, one platform, one set of assumptions. Against 6 platforms, 6 physical systems, 6 independent teams, spanning 15 orders of magnitude in scale, agreeing not roughly, but exactly with one compact theory's predictions?
At some point, refusing the conclusion stops being caution and becomes its own extraordinary claim. The claim that 6 unrelated conspiracies of error in superconductors and diamonds and beams of neutrinos all counterfeit the same rival theory by coincidence. What does it mean that the intuition every human is born with now requires to survive more conspiracies than the strangeness it was protecting you from?
And in a final twist of the knife, experimenters found that even quantum theory's own ceiling can be raised. The 3/2 maximum for K3 holds for genuinely 2 valued measurements, but give the system 3 accessible levels instead of 2, and theory permits the correlator to climb toward its absolute arithmetic maximum. The experiments followed. 3-level tests have measured K3 at 1.97 against a theoretical limit of 2, quantum mechanics saturating not just the classical bound, but nearly the outermost value arithmetic itself allows, with companion witnesses of coherence pinned at their own maxima. The innocent picture's ceiling was 1. The measured world sits at 1.97. This is not a phenomenon at the edge of detectability, teased out of noise. It is a chasm, measured to 2 decimal places, between the world's bookkeeping and the bookkeeping of definite things, and it grows wider the more carefully anyone looks. Which forces the question that has been pacing behind every experiment tonight, and it is time to face it at full size. If the definiteness we trust is nowhere in the small world, how large does something have to get before the quantum options collapse into one honest fact? What is the biggest object ever caught being 2 things at once? The answer, as of the current record, has 2,000 atoms in it, and the story of how it was caught belongs to a machine in Vienna that gives solid matter the same treatment light got 400 years ago. The machine is a Talbot-Lowe interferometer in Marcus Arndt's laboratory in Vienna, and its mission is brutally simple: send ever larger objects through the double-slit logic, the founding ritual of quantum mechanics, and see when, if ever, the interference stops. Interference is the tell. A definite object takes one path and lands where ballistics says. A quantum object's possibilities traverse the alternatives together and write a striped pattern no definite path story can produce. In 1999, the Vienna group made fullerenes interfere, soccer ball molecules of 60 carbon atoms, already outrageously large by the standards of the founders. By 2013, the record stood above 10,000 atomic mass units. And in September 2019, Yakov Fine, Arndt and colleagues published the current summit, custom-synthesized oligoporphyrin molecules, deliberately engineered, sprawling structures, some with more than 2,000 atoms, masses beyond 25,000 daltons. One specimen's chemical formula runs to 707 carbons, 908 fluorines. Launched through the interferometer, these molecules, each one a small world of bonded matter, heavier than some proteins, produced clean interference stripes, holding their quantum superposition for more than 7 milliseconds of flight. 2,000 atoms, behaving as one delocalized possibility cloud, refusing, measurably, repeatably, to take a single path through the machine. Every year the record climbs, and every year the innocent picture's territory shrinks from below. Now calibrate, because tonight refuses to oversell even its best numbers. 25,000 daltons is monstrous by quantum standards, and nothing by yours. A fleck of dust, the smallest thing your eye can catch drifting in a sunbeam, outweighs those record molecules by something like 20 orders of magnitude. The march up the mass ladder has been relentless, and it has covered perhaps half the logarithmic distance from the atom to the everyday. The remaining half is where every hard question lives. So it is worth hearing how the marchers themselves describe the road ahead. And there is a sentence from Arndt and the theorist Klaus Hornberger in Nature Physics that this channel regards as one of the most quietly astonishing admissions in modern science.
It is an intriguing open question, they wrote, whether the linearity of quantum mechanics extends into the macroscopic domain. And, they added, progress inspires hope that the debate may be settled by tabletop experiments. Read the first half again. Whether the arithmetic of superposition, the rule that would, unchecked, put chairs and coins and moons into combinations of states, actually holds at your scale is an open question. Not settled by the chair's evident solidity, the founders of decoherence theory will explain shortly why solid appearance is exactly what a quantum chair would present. Open. In the standing professional judgment of the people running the frontier experiments, the question Einstein asked on that walk, "Is the moon definitely there?" has not been answered. It has only, at last, become askable. And if there is a border on that remaining half of the ladder, what could it even be made of? Audit the candidates, because their poverty is the point. Size? Nothing in the equations contains a length beyond which superposition switches off. And the neutrino result stretched quantum correlations across 700 kilometers. Mass? That is the collapse theorists' wager, and it is genuinely open. But it requires new physics, new constants, new terms in the master equation. The existing theory offers no threshold. Complexity, some special density of interconnection? No equation of physics so much as defines the word. Temperature, wetness, biology? The robin in the next paragraph has something to say about that. Every intuitive border dissolves on inspection into either no known mechanism or new physics required, which is why the question is genuinely, professionally open rather than merely unfashionable. The innocent picture is not waiting comfortably behind a wall somewhere up the ladder. No wall has ever been located, and nobody can currently say what a wall would be built from.
The strangest recruit in this story, though, may already be alive, warm, and flying over your house. For decades, a puzzle in biology, migratory songbirds, European robins are the classic subjects, sense the direction of Earth's magnetic field, a field about 100 times weaker than a refrigerator magnet's grip, with no known organ that should feel it. The leading explanation, now backed by a web of chemical and behavioral evidence, is called the radical pair mechanism, and it is quantum to the bone. Light striking proteins in the bird's eye produces pairs of electrons whose spins dance in entangled superposition, and the Earth's faint field biases that dance, tilting the chemistry that follows. A compass whose needle is a coherent quantum state inside a living cell. Theorists analysing the behavioural data argued the dance must persist for tens of microseconds to explain the bird's sensitivity, durations that, at the time, exceeded what human engineers sustained in comparable molecules cooled to near absolute zero. Direct spin resonance work has since pushed back with an upper bound below 10 microseconds, and the tension between those numbers is an active, unresolved research front, documented here as a dispute, not a verdict. But the framing alone earns its place tonight. While physicists in shielded, cryogenic laboratories fight decoherence to keep a superposition alive for milliseconds, evolution may have been running room-temperature quantum coherence in wet, warm, living tissue, in a sparrow-sized head in daylight, for millions of years. What does it mean that the divide we assumed between the quantum world and the lived world may be violated nightly, over your roof, by a bird? So the mass ladder stands half-climbed, the experiments crowd upward, and nothing anywhere on it has behaved classically when tested properly. And yet, your coin remains stubbornly, perfectly definite every time you check. Both facts are data. The rest of tonight is about the three ways physics has of holding them together. The loophole that lets definiteness survive below the radar. The interpretations that redraw what definite ever meant. And the boldest option of all, actual new physics. A real mechanism that murders superpositions as objects grow, hunted right now by detectors buried under mountains and satellites falling silently around the sun. Begin with the loophole, because it is the honest hinge of this entire subject. The reason tonight's title says more than the data strictly allow.
and the reason every careful physicist in this field chooses their words like a lawyer at a murder trial. Recall the two assumptions the 1985 trap was built from, and notice, as the field itself took years to fully internalize, that a trap built from two planks can only ever break their combination. Assumption 1. The system is always actually in a definite state. Assumption 2. Its state can be checked without deflecting what follows. When the inequality shatters, logic offers the survivor a choice of funerals: bury definiteness or bury gentle checkability. Every headline, including tonight's title, buries definiteness. The world dissolves when unobserved. But a macrorealist of iron discipline can attend the other funeral instead. The current was always definite, the atom was always somewhere, and your measurements, every one of them, including the ones consisting of no interaction at all, were secretly invasive in ways your control experiments failed to capture. This is the clumsiness loophole, named with deliberate mischief by the theorists Mark Wilde and Ari Meisel, who also proved the sharpest thing known about it. It cannot be closed with logical finality. Ever. Their adroit measurement protocols, decomposing a measurement into steps, each certified harmless in dedicated control runs, can narrow the hatch until the surviving skeptic must claim that individually innocent steps conspire to disturb only in combination, a position with the epistemic dignity of a getaway driver, explaining that each turn was legal. The Bonn experiment's detector silence trick narrows it further still. But narrowed is not sealed. A macrorealism defended by unfalsifiable clumsiness is a doctrine that has stopped doing science, yet it is not strictly refuted. Tonight owes you that sentence with no music behind it. And there is a second survivor at the funeral, stranger and more instructive, because it is not a loophole but a fully constructed physical theory. Bohmian mechanics, the pilot wave theory this channel has visited before, is a flatly realist account of the quantum world. Every particle possesses a perfectly definite position at every instant, no exceptions, guided along its trajectory by the wave function. It reproduces every quantum prediction, which means it violates the leggett-garg inequality, while being a theory of objects that are always, definitely somewhere. How does a realist theory break an inequality that definiteness was supposed to guarantee? By cheerfully demolishing the other plank. In Bohmian mechanics, measurement is never non-invasive. The guiding wave laces the measured system to the measuring device. Checking a particle's state reconfigures the wave that steers everything afterward. Gentleness is structurally impossible. Bohm is the living proof, formalized in the philosophical literature as the disjunction problem, that the experiments of the last hour license precisely one conclusion: the conjunction is dead. Definiteness plus gentleness cannot both survive. Which one died in your universe is, as of tonight, a choice the data cannot make for you. So when this video's title says the world dissolves when unobserved, hear it as the prosecution's closing argument, not the verdict. It is one of the two readings left standing, the one most physicists lean toward, not the one the arithmetic compels. Honesty done, here is why most physicists nonetheless decline the macrorealist funeral arrangements. The clumsiness defense must be reinvented ad hoc for every new system. One conspiracy of disturbance for superconducting currents, a different one for cesium atoms, another for diamond spins, another for neutrinos crossing 700 kilometers of rock. Each conspiracy must be calibrated to mimic, exactly, the predictions of one compact quantum formalism that covers them all with no conspiracies at all. At some point, the defense's collected paperwork weighs more than the alternative worldview it resists. And the Bohmian survival, though genuine, purchases realism at a price tag the buyer must read, an explicitly non-local wave steering every particle instantaneously across the universe, an invisible layer of definite trajectories that no experiment can, even in principle, ever confirm to be there. What does it mean when the only ways to keep the world definitely there are to postulate either an undetectable conspiracy of disturbances or an undetectable web of trajectories? It means, at minimum, this: Naive there-ness, the free, obvious look-and-see kind your thumb takes for granted on the coin, is gone from physics, and everything that might replace it costs something. The remaining questions are about the bill, and before the final reckoning of who pays what, the trial has one more courtroom to visit, the strangest of them all. Because in 2019, an experiment in Edinburgh stopped asking whether unobserved properties exist and started asking a question one floor deeper. When two observers watch the same event, does physics guarantee they inhabit the same facts? The answer arrived at 5 standard deviations, and it is the closest this subject has ever come to genuine vertigo. Since the whole dispute now funnels through the single word, gentle, it is worth seeing concretely how experimenters certify gentleness, because the craft here is as ingenious as any physics tonight, and it is the difference between a loophole that gapes and a loophole squeezed to a crack. The first tool is a condition with a telling name: no signaling in time. The idea is disarmingly simple bookkeeping. If your earlier measurement truly does not disturb the system, then the statistics of any later measurement must come out identical whether or not the earlier one was performed. So run the protocol both ways, with the intermediate measurement and without, and compare the final tallies. Any macrorealist worth the name must agree this is a fair audit. In a world of definite states gently read, reading versus not reading upstream cannot reshuffle the downstream numbers. Quantum mechanics, of course, predicts that it can. Measurement redistributes the possibilities even when it is as soft as theory allows. And the audits confirm the reshuffling with the same brutality as the inequalities themselves. The second tool is the quantum witness, a single number distilled from that comparison, the gap between the later statistics with and without the earlier interrogation. For a 3-level system, arithmetic caps the witness at 2/3. Laboratory values have reached 0.65, plus or minus 0.02. Absorb that. The measured disturbance signature sits within 3% of the largest value any conceivable theory allows. Nature is not merely violating the classical audit, it is maxing it out. The third tool is the Wild-Meisel Adroit protocol, and it deserves a slow look because it is the field's most direct answer to the clumsiness charge. The strategy: never ask the skeptic to trust a measurement. Decompose it. Break the interrogation into elementary steps, and for each step run a dedicated control experiment on states specifically prepared to expose disturbance. States for which that step, if invasive, would leave fingerprints in the statistics. Certify step 1 harmless in the data. Certify step 2 harmless in the data. Then run the full sequence. And when the inequality still shatters, present the skeptic with their remaining position. Their claim must be that operations individually certified innocent, in your own audited controls, somehow conspire to disturb only when performed in combination, and to disturb by precisely the amount quantum mechanics predicts, for reasons having nothing to do with quantum mechanics. This is the checkmate-adjacent structure of the modern experiments. The Diamond 3-box game and the Flux Qubit tour de force both carry these control audits in their published bodies. And still, say it plainly one more time because the integrity of the whole night depends on it. The position survives as logic. Conspiracies of exactly compensating disturbances cannot be excluded by any finite set of controls. Wild and Meisel proved the hatch stays ajar as a matter of principle. What the protocols accomplish is not closure, but cost accounting. Each audit multiplies the coincidences the surviving macrorealist must posit, until the doctrine's price rises from a reasonable caution about clumsy instruments to a precisely tuned, universal, undetectable choreography of errors mimicking one rival theory's every prediction. Doctrines are rarely refuted in this business. They are priced out. And here a viewer with a good memory will hear an echo, because this channel has stood at an almost identical crossroads before, one flight down. Bell's theorem faced its own loopholes: detection efficiency, communication between stations, freedom of choice. and its history became a decades-long campaign of closures, culminating in the loophole-free tests of 2015 that this channel has told in full. The leggett-garg program is that same story, transposed from space to time, with one structural difference the honest ledger must record. Bell's spatial loopholes were, one by one, fully closable, and were closed. The temporal analog's central loophole, clumsiness, is provably not fully closable, ever, because measurements on a single system across time can never be space-like separated from that system, the way two distant stations can be separated from each other. You cannot put an atom's Tuesday outside the light cone of its Monday. That asymmetry is why the space version of quantum weirdness was settled to essentially universal satisfaction within 51 years of Bell's paper, while the time version, tonight's version, the one that touches your coin, remains, 40 years in, a matter of overwhelming evidence and no final decree. The universe permits airtight verdicts about what is forbidden between distant places. About what exists across moments of time, it has left us, perhaps permanently, one notch short of certainty, as if the past of a thing were the one witness that can never be fully cross-examined.
The courtroom was built from a thought experiment 60 years old. In 1961, Eugene Wigner imagined a friend performing a quantum measurement inside a sealed laboratory. Inside, the friend sees a definite outcome. The detector fired, or it did not. A fact recorded in a notebook. Outside, Wigner, treating the entire laboratory, friend and notebook included, as one quantum system, as the linearity of the theory instructs, must describe it as a superposition. Friend who saw yes entangled with friend who saw no, no definite fact yet in existence. Two impeccable applications of quantum mechanics. One event, two contradictory accounts of whether an outcome has even occurred. For decades, this stayed a philosopher's exhibit, safely hypothetical because no one could put an observer in superposition. Then theorists sharpened it into arithmetic. A 2018 no-go theorem by Daniela Frautschiger and Renato Renner proved that quantum theory, applied to agents reasoning about each other's measurements, generates flat contradictions unless something cherished is abandoned. Their own dry conclusion was that quantum theory cannot be extrapolated to complex systems, at least not in a straightforward manner. And in 2019, Massimiliano Proietti, Alessandro Fedrizzi and colleagues at Heriot-Watt University in Edinburgh did the thing this field always eventually does. They built it. 6 entangled photons, 2 serving as the measured systems, 2 standing in as the friends, minimal observers that irreversibly register outcomes, and 2 as the external super-observers. The experiment stages, physically, the clash between the friend's recorded facts and the outsider's superposed description, and packages the clash into a Bell-type inequality that any observer-independent notion of fact must satisfy. Measured result, violated by 5 standard deviations. The published conclusion, in the author's own words, if one holds fast to locality and free choice, the result implies that quantum theory should be interpreted in an observer-dependent way. Let the meaning of that land without theatrics, because stated carefully, it is heavier than any theatrics could make it. The experiments earlier tonight undermined properties, where the atom is, which way the current flows. This experiment undermines facts. Whether an outcome has happened can itself carry an according to whom. 2 honest, error-free observers can generate records that no single objective story reconciles, and physics, as currently written, does not adjudicate between them. It certifies both. The comfortable dismissal, surely this is wordplay about photons, not about observers, is precisely what the escalation from thought experiment to laboratory keeps eroding. The friends in Edinburgh were single photons, yes, but nothing in the theorem's logic caps the size of the friend. Run the same construction with a friend made of neurons instead of silicon and photodiodes, and quantum mechanics offers no line, none, where its verdict changes. Either something stops the logic before it reaches people, or what happened is, at bottom, perspectival. Every option on that menu is expensive, and you have met the menu before tonight.
Perhaps superpositions physically die before reaching observer scale, new physics. Perhaps all outcomes occur in branching worlds. Perhaps quantum states were never descriptions of reality at all, only of each observer's information, in which case the friend's fact and the outsider's superposition were answers to different questions and never contradicted. What does it mean that the cheapest reading of our best physical theory now prices objective fact as an optional extra? Head off immediately. The misreading this result always invites. None of this says reality is whatever anyone believes, and none of it licenses the shop-worn mysticism that observation conjures the world. The disagreement between Wigner and his friend is not a disagreement of opinion. It is generated by the theory's own machinery, under conditions so extreme that no human pair will ever occupy them. It requires one observer to maintain perfect quantum control over another observer's entire laboratory, every atom coherent, every record reversible. The moment the laboratory leaks, one photon escaping, one molecule of air warmed, decoherence welds the two accounts back into one, which is why every actual pair of humans in history has always agreed about every actual outcome. The vertigo is not that your neighbor might inhabit different facts about today's breakfast. Decoherence forbids it with astronomical margin. The vertigo is structural. The theory that underwrites all of chemistry and electronics turns out to contain no theorem guaranteeing observer-independent facts. The agreement we observe is enforced by thermodynamic circumstance, not by law. Objectivity in quantum mechanics is not a foundation. It is a phenomenon, real, robust, and, in the theory's fine print, negotiable under conditions the universe rarely grants. Notice where the pressure has finally come to rest, because the whole night has been quietly converging on one word. Not where is the atom, not which way does the current flow. The word is measurement, the process this entire subject is named after and has never once defined. Every inequality violation tonight was a fact about what happens when measurements occur. The clumsiness loophole is a dispute about what measurements disturb. The Wigner's friend vertigo is a dispute about when, if ever, a measurement has finished happening. A century after the founders, quantum mechanics remains a theory that predicts the statistics of measurement outcomes flawlessly, while containing no equation that says what a measurement is, which physical processes count, or why exactly one outcome emerges from each. That scandal has an official name, the measurement problem, and physics has exactly one response to it that rises above interpretation and re-enters the laboratory. The possibility that collapse is not a mystery of observers at all, but a physical process, real, objective, mass-dependent, happening everywhere all the time, whether anyone looks or not. If that is true, the definiteness of your coin is not a philosophical embarrassment. It is a measurable force of nature. And the hunt for it, under a mountain in South Dakota, in a tank of liquid xenon in Italy, aboard a spacecraft a million miles from home, is where this story stops being about interpretation forever. The idea is called objective collapse, and its founding gambit, published in 1986, 1 year after the leggett-garg paper by Giancarlo Girardi, Alberto Rimini, and Tullio Weber, solves the measurement problem by the most direct method imaginable. It changes the equation. The Schrödinger equation, as written, is linear and universal. It never collapses anything, ever, which is precisely why it predicts cats and friends in superposition and leaves measurement undefined. So GRW, as the theory is known, adds to it a new term of nature. Every fundamental particle, everywhere, at all times, has a tiny fixed probability per second of spontaneously localizing. Its spread-out wave of possibilities snapping, at random, into a sharply defined position about 1/10 of a micron across. No observer required, no measurement postulate. Collapse is simply a thing matter does, rarely, like radioactive decay. And the rate is chosen with surgical cunning, roughly once per 10 to the 16 seconds per particle. For a single electron or atom, one spontaneous snap every 300 million years, which is why every atomic scale experiment ever performed sees perfect, unbroken quantum behavior. But bind 10 to the 23 particles into a coin, and entanglement makes the snaps collective. Any single particle's localization drags the whole object's state with it. And with that many lottery tickets, something in the coin snaps within nanoseconds. Permanently, continuously, faster than any instrument could ever catch it blurred. Small things, quantum forever. Big things, definite always, as a matter of physical law. The border between the atom and the coin that tonight has been hunting? GRW says it is real, it is arithmetic, rate times particle number, and it sits, deliberately, in the mesoscopic no-man's land the experiments have been climbing toward. Philip Pearl smoothed the random snaps into a continuous version called CSL, Continuous Spontaneous Localization, which is the form experimentalists actually test, and the night's third equation is its schematic heart. Before the symbols, it is the ordinary Schrödinger equation plus interlopers. The equation reads d psi equals minus I over h bar h psi dt, the familiar linear reversible part, plus stochastic noise terms, plus a non-linear localization term. Everything strange about tonight lives in those two added terms. They are random where quantum mechanics is deterministic, non-linear where it is linear, and irreversible where it is time-symmetric. They are also, and this is the entire point, consequences-bearing. Real terms in a real equation of motion produce real, measurable side effects, and side effects are things laboratories can hunt. The second collapse theory on the table replaces GRW's arbitrary constants with the oldest force in physics. Laios Diosi in 1989 and Roger Penrose in 1996, working independently, proposed that gravity itself is the assassin of superpositions. Penrose's argument has a beautiful, almost geometric inevitability. A massive object in two places at once is, by general relativity, two different space-time geometries in superposition. And nature, he argued, cannot sustain a superposition of spacetimes for long. The deeper the gravitational mismatch between the two branches, the faster the structure must resolve into one. The night's fourth equation prices the survival time, and it is the shortest formula of the evening. Before the symbols, a superposition lives for Planck's constant divided by the gravitational self-energy of the difference between its two mass arrangements. The equation reads tau equals h bar over Eg. For an electron in two places, the gravitational mismatch Eg is so minuscule that tau stretches beyond the age of the universe. Electrons superpose freely, as observed. For a dust grain in two places a millimeter apart, tau collapses to a fraction of a second. For your coin, instants beyond reckoning. The elegance is what seduces. No new constants of nature. The collapse rate is set by Newton's G, already measured. A genuine unification instinct, wiring the definiteness of the everyday world directly to the curvature of space-time. Diosi's version, worked through in detail, needs one technical mercy: a smallest length cutoff below which the mass distribution is smeared. And where that cutoff sits will turn out, within a few minutes of tonight, to be the theory's exposed throat. Ask the question that makes collapse theories feel real. If GRW were true, what would be different about your morning? And sit with the answer, because it is the whole reason the theory is viable. Nothing. Not one thing. Your coffee, your commute, your coin. Identical in every detail, because the theory is engineered to leave the tested world untouched. Atoms quantum, objects definite, the crossover parked exactly in the unmeasured middle. Is that a virtue or a confession? Both, and honestly so. It is a virtue because a proposal that changed tested physics would already be dead. It is a confession because a theory whose signature hides precisely where nobody has looked invites the obvious suspicion. Convenient that the new physics lives only in the gap. What rescues GRW and its cousins from being mere wishful bookkeeping is the thing the next chapter is made of. The gap is shrinking, measurably, year by year, and the theories cannot move. Their parameters are pinned between two cliffs. Collapse fast enough to definitize the mesoscopic world, or fail at your coin. Collapse slowly enough to spare the atom, or contradict a century of data. A theory pinned between cliffs is a theory you can hunt. What does it mean that the one mechanism which could make your world definite without observers has been backed by its own logic into a corridor with instruments waiting at both ends? Stand back and see what the collapse theories offer, because within tonight's trial, they are a genuinely different kind of animal. Every interpretation you will meet in the final act, many worlds, Bohm, the epistemic readings, agrees exactly with standard quantum mechanics about every experiment forever. Choosing among them is, by construction, beyond the reach of any instrument. GRW, CSL, and DOC Penrose are not interpretations. They are rival physical theories that contradict quantum mechanics, slightly, quantitatively, in regimes not yet fully tested, and their deviations are specific enough to arrest. 3 fingerprints, above all. First, the interference ceiling. Since collapse strengthens with mass, there is a molecular size beyond which Vienna-style interferometers must watch the stripes fade, no matter how perfect the vacuum. A hard prediction the mass ladder march tests with every rung. Second, spontaneous heating. The endless random localizations jiggle matter, injecting a faint, universal warmth into everything, everywhere. Detectable in principle as anomalous noise in exquisitely cold, quiet systems. Third, the strangest and most decisive, spontaneous radiation. Snap a charged particle's wave function and the jolt makes it radiate. Matter obeying CSL or DOC Penrose dynamics must glow, very faintly in X-rays, with no energy source. Every kilogram of ordinary silence emitting a whisper of photons that standard quantum mechanics flatly forbids. 3 fingerprints, all quantitative, all wired to the same dials, the collapse rate and the cutoff, which means every quiet detector on Earth that fails to see them shrinks the theory's allowed territory on a map. That map exists. It is drawn in a plane of collapse rate versus correlation length, its axes logarithmic, its white regions alive and its shaded regions executed. And for the last decade, 3 of the most sensitive machines our species has ever built have been shading it, closing in on the original proposals from 3 directions at once. One of the 3 machines was not even built for this. It was built to prove a spacecraft could fall perfectly, and it became, by accident, the best collapse detector in the solar system. The spacecraft was LISA Pathfinder, launched by the European Space Agency in December 2015 to rehearse the technology for a gravitational wave observatory in space. Its cargo was 2 small cubes of gold-platinum alloy, floating free inside the craft, shielded from sunlight, solar wind, and every disturbance engineering could exclude. The most perfect freefall ever achieved. Their relative acceleration monitored to femtometers per second squared, quadrillionths of a meter. The mission was a triumph of quiet. And quiet, it turns out, is exactly what collapse theories cannot tolerate. If CSL's random localizations are real, the cube's atoms are being ceaselessly, microscopically kicked, and 2 free-floating test masses must jitter with a specific extra noise that no shielding can remove, because the noise comes from the dynamics of matter itself. Theorists combed Pathfinder's acceleration data for that jitter and found none, down to the mission's exquisite flaw. The silence converts directly into borders on the map. The CSL collapse rate cannot exceed a few parts in 100 million per second. a bound cutting straight through the middle of the enhanced parameter region that theorist Stephen Adler had argued was needed for collapse to do its job at realistic scales. And for DOC Penrose, the same silence forces the theory's cutoff length above 40 femtometers, larger than any atomic nucleus. Hold that number a moment. The gravitational collapse theory survives only if the mass of a nucleus is smeared over a region bigger than the nucleus itself. The theory's natural, physically motivated choice of cutoff, the scale of the particles actually carrying the mass, is dead. Killed not by a philosopher's argument, but by two golden cubes falling silently through space, doing nothing, perfectly. Notice, before the second machine, a pattern worth loving about this hunt. Not one of its instruments was built for it. Why is the search for collapse conducted entirely by borrowed equipment? Because collapse's fingerprints, anomalous jitter, sourceless warmth, unexplained X-rays, are exactly the phenomena that every precision experiment on Earth already treats as its worst enemy: noise. The machines built to detect gravitational waves, dark matter, and impossibly rare decays are, by construction, humanity's greatest catalogues of what does not happen in quiet matter. And a theory whose signature is a faint, universal something happening can be executed by any sufficiently authoritative catalogue of nothing happening. The physicists hunting the rarest events in the universe are, unavoidably, also auditing the metaphysics of definiteness, most of them without ever intending to. The second machine was built under a hill in South Dakota to search for one of the rarest conceivable nuclear decays, and its virtue is purity. The Majorana demonstrator, 44 kilograms of germanium crystals of heroic radiological cleanliness, watched for 4 years by detectors capable of registering a handful of unexplained X-ray photons per year. Unexplained X-rays are, remember, collapse theory's third fingerprint. CSL and DOC Penrose dynamics require the germanium's own electrons and nuclei to glow spontaneously, source-free, in exactly the energy window this instrument patrols. Result, published 2022, no glow. Backgrounds fully accounted, nothing left over for collapse. The bounds tightened 40 to 100 times over every previous radiation search, and for DOC Penrose, the throat cut deepened. The cutoff length was forced above 1/4 of a nanometer, atomic scale, thousands of times the size of a nucleus, and 50 times beyond Penrose's own suggested value for the crystal. The parameter-free gravitational collapse theory is now surviving only in a smeared, softened form, drifting ever further from the elegant original. And the third machine delivered the freshest wound of all. XENONnT, several tons of liquid xenon in Italy's Gran Sasso laboratory, built to catch dark matter, currently the quietest low-energy photon detector on Earth. Published this year the most sensitive spontaneous radiation search ever performed. Its analysis accounted for the first time for a subtle cancellation between the radiating charges in xenon atoms that had flattered earlier bounds. The verdict? CSL limits improved by 2 orders of magnitude, DOC Penrose by a further factor of 5, and, for the first time, the original CSL parameter values proposed by Ghirardi, Pearl, and Rimini themselves are excluded. The founding numbers of continuous spontaneous localization, the actual dials the theory shipped with, are now dead territory on the map. Be precise about the score, because this hunt is frequently reported with either too much triumph or too little. Collapse theories are not dead. The parameter map still holds living territory. The original GRW rate, slower than CSL's, radiating differently, survives in part. Softened DOC Penrose variants persist, and the space between the excluded islands remains genuinely open, which is why the hunters keep hunting. Proposals now circulate for spaceborne interferometers and levitated nanoparticles that would push through much of what remains within a decade or two. Angelo Bassi, the field's most prominent living advocate, co-author of the Standard Reviews, states the situation with a candor tonight is happy to amplify. Whether the superposition principle applies to macroscopic systems or instead breaks down progressively at larger scales is a fundamental and still open question. That is the state of the art from the theory's own champion. Open. But feel what a strange and wonderful thing has happened to Einstein's walking question inside this chapter. Because it is tonight's quiet triumph regardless of who wins. Is the moon there when nobody looks? For a century, the textbook answer was that the question is unanswerable, meaningless, outside science. And now, two golden cubes in space, a germanium array under a hill, and a tank of xenon under a mountain are answering it. Not with opinions, with exclusion plots. If matter definitizes itself, the process radiates, jitters and heats, and we are measurably closing in on where its dials could sit. If the detectors stay silent all the way down the map, collapse dies, and with it the last mechanism for a world that is definite without observers. Either outcome is a discovery of the first rank. The question your thumb settles every time you check the coin, how does one outcome happen, has become an experimental program with a budget. What does it mean that the metaphysics of your kitchen table is currently being decided, photon by absent photon, in the quietest places human beings have ever built? Before the final reckoning, one massive piece of the puzzle must be set in place. The piece that explains why, whatever the truth about collapse, your coin will never once be caught blurred. It is called decoherence. This channel has walked its full length in another night, and tonight needs only its verdict, but stated with a precision the popular versions always fumble. A quantum superposition survives only while its alternatives remain private. The instant information about which alternative leaks into the environment, one photon bouncing differently off heads than tails, one air molecule recoiling differently, the interference between the alternatives is destroyed, and the system's statistics become indistinguishable from those of an ordinary, definite but unknown fact. And for anything coin-sized in any environment warmer than deep space, the leak is not slow. Scattering calculations put the decoherence of a dust grain's position at trillionths of a second, the fastest process in the known universe, faster than any conceivable instrument, over before has meaning. This is why the mass ladder march is so brutally hard. Vienna's interferometers succeed by heroic isolation, starving the environment of which path information for milliseconds. And it is why every macroscopic object you have ever met presents an immaculately definite face. The environment is measuring the coin, relentlessly, redundantly, trillions of times per second, whether or not any person ever does. Wojciech Zurek's quantum Darwinism completes the picture. The environment does not merely destroy coherence, it broadcasts the surviving alternatives, copying the coin's position into billions of scattered photons. That is why you, and a friend, and a fly on the wall all agree about where it sits. You are all reading independent copies of the same environmental record. Observation, in this account, was never special. It is just late arrival at a measurement the universe performed first. So decoherence explains the appearance of your definite world, fully, quantitatively, with no new physics. And now the fine print, delivered by the theory's own architects, which is the pivot on which tonight's entire final act turns. Decoherence does not explain why one outcome happens. Listen to the principles, because on this point they are unanimous and blunt. Zurek, who built the framework, decoherence does not, by itself, solve the measurement problem. Maximilian Schlosshauer, author of the Standard Treatise, decoherence achieves the transition from quantum superposition to classical mixture, but not the further step from the mixture to a single definite result. Understand exactly what is and is not delivered. Decoherence explains why you will never see interference between coin heads and coin tails, why the alternatives stop talking to each other. It does not explain why, on this particular occasion, the world contains heads rather than tails. In the unbroken mathematics, both alternatives persist, decohered, non-interfering, each entangled with its own consistent environment, its own records, its own version of you. The formalism hands over a perfectly weighted menu and no mechanism for the choosing. And every deep divide in this subject is, at bottom, a different theory of the choosing. Say the problem in one sentence, because it is the honest edge of this entire topic, the one question every path tonight has led to. Physics does not currently know why any single, definite outcome ever occurs, or whether single is even the right description of what does. Your thumb on the coin executes, every time, flawlessly, an operation that no equation in physics yet describes. And grasp the scale of the environmental bookkeeping, because the environment measures the coin is not a figure of speech. It is an accounting with numbers attached. Every second, roughly a billion photons strike a coin-sized patch of any ordinary room. Sunlight, lamplight, the infrared glow of the walls themselves. And every one of them departs carrying a faint imprint of the coin's position, orientation, face. Air molecules collide with its surface trillions of times per microsecond, each recoil another record. Within a nanosecond of any conceivable displacement, the information, the coin is here, not there, exists in more independent physical copies than there are humans who have ever lived. And the copies are already dispersing at the speed of light. Could you, with unlimited technology, intercept and erase every record before it spreads? Restore the coin's quantum privacy, catch it undecohered. Run the numbers and the answer is a flat no. The records multiply faster than any physical process could collect them, forever. That is what the definiteness of your world is in the Decoherence account. Not a property matter carries in its pocket, but a broadcast too redundant to recall. Feel how strange the final standing of your coin has become, caught between the two halves of tonight. From below, the leggett-garg campaign, 5 sigma, 6 sigma, 84 sigma, has demolished the assumption that things like it are definite all the way down, and found no flaw where definiteness begins. From above, decoherence guarantees that nothing coin-sized will ever be caught in the act of being indefinite. The evidence is erased faster than any instrument can exist. The innocent picture is provably false below and perfectly protected above, and the protection is itself a quantum mechanical effect. The coin is defended by the very physics it seems to refute. What does it mean that the world's solidity and the world's strangeness turn out to be the same mechanism, viewed from its two ends? Whatever your answer, this is the completed evidence table. The violations, the loophole, the observer-dependent facts, the collapse hunt, and decoherence's magnificent, incomplete explanation. Every fact is now on it. What remains is what this channel always saves for last, the weighing. A dozen live readings of what it all means, no referee, and one honest accounting of which survivors pay which bills. The weighing begins with the incumbent. The Copenhagen reading, the textbook default since the founders, says the quantum state is a calculational device that collapses upon measurement and declines, on principle, to say what measurement is or what exists between them. Its case? It has matched every experiment for a century, and its refusal to over-describe may be wisdom rather than evasion. Its bill? The refusal sits exactly where tonight's experiments now drill. Wigner's friend and the leggett-garg campaign keep converting Copenhagen's polite silence into visible contradictions between observers. A default that answers "when does collapse happen?" with "when it is convenient to say so" was sustainable when the question was philosophy. It is less so now that the question has error bars. Next, the objective collapse family, GRW, CSL, DOC Penrose, the night's only rivals that fight as physics rather than philosophy. They solve the problem of outcomes completely, observer-free, and they pay the steepest possible price for the privilege: falsifiability. The golden cubes, the germanium and the xenon are collecting on that price, island by excluded island. Respect what that wager is, the one family that could make your coin definitively, physically definite, has agreed to die by experiment, and is dying by degrees. Not dead, but cornered, its founding parameter values already gone. Then the Everett reading. No collapse, no choosing, every outcome real in its own decohered branch. The menu is never trimmed, and the appearance of single outcomes is what a branch feels like from inside. Its case, it is just the unbroken equations, taking Decoherence's fine print at face value, nothing added at all. Its bill, a universe of perpetually multiplying versions of you, and a still unresolved struggle to say what probability even means when everything happens. Then Bohm, the realist survivor, definite positions forever, purchased with undetectable trajectories and explicit non-locality. And then the readings that dissolve the problem rather than solve it, the epistemic family. Cubism holds that the quantum state was never a description of the world at all, but of an agent's expectations. Collapse is just updating, like a gambler revising odds, and Wigner and his friend hold different states because they hold different information. No contradiction, no dissolving world, nothing was ever out there blurring. Its power is real, and it has a startling exhibit. Robert Speckens built a toy theory, ordinary classical physics plus one rule, that you can never know more than half the facts, and out-tumbled 24 signature quantum phenomena, no cloning, teleportation, interference-like statistics, remote steering. If mere ignorance with a cap mimics that much of quantum mechanics, perhaps the quantum state really is closer to knowledge than to substance. But mark what the toy could not reproduce: Bell violations and contextuality, the phenomena at the heart of tonight, which are, by that very failure, certified as the genuinely, irreducibly quantum residue, the part of the world that no story about limited knowledge of definite facts will ever cover. Relational quantum mechanics rounds out the family. Facts are real but relative to the system that registered them. Wigner's friend made into a metaphysics. Its open wound, explaining why observers comparing notes always, in practice, agree. And at the fringes, two mirror image desperations. Consciousness causes collapse, which this channel examined on another night, and which founders on a universe that ran 13 billion years before any awareness. And superdeterminism, which saves definiteness by proposing the universe's initial conditions conspired to correlate every experimenter's choices with every particle's state. Logically airtight, scientifically inert.
Before the referee's card, hold the menu up to yourself, because the honest way to read it is as a price list for your own three-part belief from the beginning of the night. Which part would you pay with? If you keep definiteness and gentle readability by buying Bohm, you pay with an invisible, non-local web no experiment can ever certify. If you keep the mathematics bare and buy Everett, you pay with uncountable diverging versions of yourself. If you buy Collapse, you pay in the currency the detectors are now counting, and may be told within decades that your account is empty. If you buy the epistemic readings, you keep every experiment and pay with the deed to the word reality itself. Quantum states describe you, not the world. Is there an option that costs nothing? There is not, that is the finding. 40 years of inequality violations have not told us which bill to pay. They have established that the bill exists, is real, and has no zero option. Every generation of physicists inherits the menu. None has yet been allowed to leave the restaurant. Which price would you pay? Hold your answer through the verdict, and notice, days from now, whether it holds you. That is the full menu, and here is the honest referee's card. Nothing on it is refuted, except the naive picture you started the night with. Nothing on it is confirmed, except the formalism they all share. The experiments of the last 15 years have not crowned a winner. What they have done, and it is historic, is redistribute the bills. Copenhagen's silence has become measurably awkward. Collapse's escape has become measurably narrow. The epistemic readings have been handed, by the Speckens toy's very success, a precise list of what they still owe. And every single reading now pays one common tax that pre-1985 physics never charged. Whatever quantum states are,
The world they describe does not consist of things with definite, gently readable properties at all times. That option, the one your instincts came in with, the one Einstein stopped on a walk to defend, is the single door the arithmetic has closed. So tonight's resolution, stated with the channel's full precision, in 3 sentences the whole evening has earned. It is established that naive realism, definite values plus disturbance-free reading, is false for every system ever tested, from single atoms to superconducting currents to particles crossing continents, at significances beyond meaningful doubt. It is established that decoherence explains, without new physics, why the everyday world nonetheless looks and behaves perfectly definite, while leaving the emergence of single outcomes unexplained. And it is not established what replaces the naive picture. Definiteness by new physics is alive and cornered. Definiteness relative to observers is alive and strange. All outcomes realized is alive and extravagant, and the experiment that separates them, unlike almost anywhere else in foundational physics, is actually running in the xenon and the germanium and the falling golden cubes. The title of tonight's video claimed the world dissolves when unobserved. The data's verdict is more precise and more haunting. The world has never once been caught holding the definite facts you assumed, and it has arranged, through decoherence, that it never will be caught lacking them either. So go back to the coin, the one you checked at the start of the night, or planned to and didn't. It is lying somewhere in the dark of your home right now, and it is time to say, with everything tonight on the table, exactly what has and has not changed about it. Nothing has changed about what you will find. Check it 1,000 times and it will be definitely heads or definitely tails 1,000 times, and anyone who checks with you will agree, every single time, forever. Decoherence has seen to that with a thoroughness no human institution will ever match. What has changed, what tonight was actually about, is your license for the word already. It was already heads before I looked. That word smuggles an entire metaphysics, a world of facts that exist unread, sitting patiently in the dark, waiting for observers who merely uncover what was there all along. Below a certain scale, that picture is not cautious common sense. It is a tested hypothesis with a 40-year record of catastrophic failure. 5 sigma, 6 sigma, 84 sigma, in diamonds, atoms, currents, and neutrinos. Above that scale, the picture works flawlessly, and physics cannot currently tell you whether it works because it is true, or because decoherence and scale conspire to make every alternative unobservable, or because facts themselves are relative to whoever holds the records. Or, finally, because a collapse mechanism nature actually possesses turns it true somewhere on the road from atoms to coins. 4 living options, 1 word, already. And after a century of the hardest thinking our species has done, no one on Earth knows which reading of it you are entitled to. Einstein's question deserves its final visit, because tonight has quietly answered a version of it, just not the one he asked. Does the moon exist only when you look at it? Rest easy, nothing tonight suggests the moon flickers out when you turn away. The sun looks at it, the solar wind looks at it, every dust grain in its shadow looks at it. In the decoherence accounting, the moon is among the most thoroughly observed objects in the history of the universe, its position broadcast redundantly into every photon that grazes it. The moon is safe. What is not safe, what died somewhere between 1985 and the xenon tank, is the innocence of the question. Einstein asked it as a reductio. Surely, if quantum mechanics implies such absurdity, quantum mechanics must be incomplete. The modern answer inverts the thrust. The absurdity has been promoted to an experimental subject, the incompleteness has never appeared, and the burden of proof has changed hands. It is no longer the quantum theorist who owes the world an explanation of why the moon seems definite. Decoherence pays that debt in full. It is the realist who owes an account of what, precisely, being there consists of, in a universe whose smallest constituents demonstrably decline to be anywhere in particular between appointments. The walk continues. The question walks with us, but it walks now on the other side of the ledger. And spare one thought for the working scientists inside this story, because tonight's cast is unusual in a way worth naming. This field's greatest doubter put his name on its most crushing experimental verdict. Its collapse theorists published the exact numbers by which their own theories could be killed, and are watching the killing proceed island by island with their names on the review papers. Its experimenters print their loopholes in their own abstracts: clumsiness quantified, disturbance audited, significance disputed openly between collaborations. Whatever the universe is doing when nobody looks, the people asking have been doing science in the open, against their own preferences, for 40 years. What does it mean that the question most likely to tempt a thinker into wishful certainty has produced, instead, one of the most self-disciplined literatures in physics? Perhaps this: the strangeness is real enough that nobody needs to exaggerate it. If a night like this one leaves you wanting the frontier rather than fleeing it, consider subscribing. It helps these deep dives reach more curious minds. And this frontier, unlike most in physics, is moving measurably, year by year, in machines that are running as you listen. Gather the stones, because tonight you carried a full expedition's worth. An inequality drawn in 1985 that converted the oldest metaphysical comfort into a number with a ceiling, and a world that has broken the ceiling in every laboratory that ever asked. A weak value of 100 from a property whose largest honest value is 1/2. An atom that crossed a lattice of light and was proven, 6 sigma by detectors that never fired, to have taken no path at all. A superconducting current driven both ways at once, whose definite flow obituary ran to 84 standard deviations, with the inequality's own inventor among the pallbearers. 2,000 atoms in 2 places for 7 milliseconds in Vienna. A robin over your roof, possibly navigating by a superposition your best laboratories would envy. 6 photons in Edinburgh holding 2 irreconcilable sets of facts, 5 sigma apart. Golden cubes falling perfectly through space, germanium under a hill, xenon under a mountain, all listening for the faint glow of a universe deciding things on its own, and hearing, so far, silence. And beneath all of it, the one question no equation yet touches. The one your thumb will execute flawlessly the next time you check. Why one outcome? This one, now. The coin is waiting. Go and look at it once more, properly this time, knowing what the looking is. Under your palm sits the entire open frontier of physics, a disk of metal whose atoms have no classical trajectories, whose definiteness no equation explains, whose steadfast, boring, utterly reliable heads or tails is either the deepest fact in the universe or the most magnificent appearance ever staged. Lift your hand. There it is, definite, certain, exactly what you expected, the way it always is and always will be. The world does not dissolve when you look away, but it has never once, in 40 years of being asked at the highest precision our species commands, agreed to say what it is doing while you're gone. Heads then, or tails. Either way, the easy yes is ruled out. No line where it comes back has ever been found. And the coin, tonight and every night, keeps the only secret in your house that physics cannot open.